Everybody, brand new topic. So up until this point, when analyzing structures, we've been trying to solve for the reactions at the joints and at the supports. So now it's time to look internal to the members of the structure. So we want to know the internal forces and moments at every point along the members of a structure. But for now, let's focus on what are the internal forces and moments at a particular point. And for this semester, let's focus on beams, and then you build up the skills and experience. So get good at studying beams, and then you can apply those skills and transfer them to other types of structural members. Like if you get really good at driving a car, it's a transferable skill if you hop into and drive a van or a truck, right? Okay, so let's say you have this beam with a pin support here and a roller here and some load somewhere in the middle. So let's say we want to know what's happening internal to the beam right here, and also say right over here. So what you do is you would section it like this. So it's like we cut it. So we cut it like this. Okay, so then so like this. Okay, and we want to know what's happening internal over here and over here. So let me just get rid of these so we can focus on that section that we cut out. Okay, so internal, so let's say like right over here, what's happening internal to the beam? There could be a number of forces and moments, but we can always reduce it to an equivalent system of one force, one couple. Now this one force I can also decompose into components, one that's along the axis of the beam and one that's normal to that. So then I can summarize it as these two force components and one couple. Okay, now which way should I draw the arrows? So nature doesn't care. For example, like what should we call the charge of an electron? Nature doesn't care if we call it positive or negative. But as a society, maybe we decide, all right, let's call it negative. Similarly, if we exist in a society of engineers analyzing structures, maybe we should all be on the same page. So then, for the axial force, we could say this way is positive. So that's compression, right? If you have a beam and you smash it, that's compression. Or the other way around, you could stretch it this way in tension. Okay, so as a society, let's call this positive. So this is the axial force, and we'll label it letter P for axial force, and we'll decide that tension is positive. Okay, so for the force normal to the axis of the beam, we could call this way positive or this way positive. So as a society, let's call this way positive, and this is called the shear force, letter V, and this way is positive, shear force V. Okay, so at this point, imagine you have a beam and you stretch it in tension. That would be called positive axial force. Imagine you, let's say, glue 4 popsicle sticks together like this. And then with your left hand, you apply a force upwards. And with your right hand, you apply a force downwards. What would happen to your square of popsicle sticks? It'll start to deform like this. So we call this positive shear. The other way around, we'll call this negative. And it seems so arbitrary, right? Because it is. It's totally arbitrary. But that's, as a society, what we decided. Okay, now for the couple over here, should we draw it this way or this way? So let's call this way positive. So this is called the bending moment. M. And then on this side, this way. Bending moment. Okay, so in other words, say you have a beam. You could bend the beam, right? Like there's a beam and then you bend it with your hands. This way or this way. So we call this way positive bending and this way negative bending. So like bending a beam to look like a happy face is positive. Bending it like a sad face is negative. I think that's a mnemonic device that I use to remember. Okay, so those are the standards. So you have to basically memorize this as the convention, since we live in a society of engineers. So this is the convention. You have to memorize it. Okay, now how do we actually solve for internal forces and moments? So here's a beam with, I'm going to draw the free body diagram. There's a pin at A, a roller at B, and a load over here. So we have kind of a coordinate system, but I'll just say, right, a coordinate system like this. So for the reaction at pin A, I'm going to decompose that into X and Y components. For the reaction at the roller B, it's like that, normal to the surface. And there's a load over here. Okay, so step 1, draw the free body diagram and solve for the reactions at the supports. So that's step 1. So let's do that. Some forces in X, some forces in Y, some torque about somewhere clever. Okay, so in the X direction, we got AX and nothing else. Y direction, AY, B, minus F. That's it. Let's sum torque about wherever we want. How about right here? About point A. So the torque, there's torque from B, which is positive in the positive Z direction. So positive L times B. Then that will be negative, and then here to here is 3/4 L, so negative 3/4 L times F, and that's it. Okay, so AX is 0, right here. B is 3/4 LF divided by L, so 3/4 F. And then that goes right here, and then AY is F minus 3/4 F, so 1/4 F. Okay, so we got the reactions at the supports. I'll just draw it again. Okay, so AX is 0, AY is 1/4 F. B is 3/4 F, and then there's a load over here. Okay, and we want to know internal forces and moments right here at point C, which is a quarter of the way over. Okay, how do we do it? So the strategy is you section it. You just chop it right there. You cut right through point C. Okay, so if we do that, there's the section on the left side and then the section on the right side, and I'll leave some space in between. Okay, so the section on the left side, what does it look like? There's still that reaction from the pin, and then on the right side, there's the reaction from the roller, and then there's a load over here, F. But then when we cut it, now we reveal what's internal to the beam. And what's the standard again? This way is axial force. this way is the shear, this way is the bending moment. Right, and then over here, this way is the axial force, this way is shear, this way is bending moment. Okay, now let's just focus on these free body diagrams. And we want to know, let's solve for the axial force, the shear, and the bending moment. Now, we don't need to solve both sections. You just pick one or the other because you're going to get the same answer either way. So whichever one looks simpler to you, that's the one you pick. So for example, I feel like this one has less because there's 1, 2, 3, 4. And then over here we got 1, 2, 3 unknowns, and then 4, 5. So there's more going on over here. So how about we go with this one? Okay, how far was that again? Quarter of the way. So 1/4 L. Here to here was 1/4 L. Okay, so how do we do this? Let's get same coordinate system. So for this free body diagram, just right, some forces, some torque about somewhere clever. Okay, so in the x direction, P, and what else? That's it. Okay, y direction, 1/4 F minus V. That's it. Okay, let's sum torque about somewhere. So we can sum torque about over here or over here. I'm gonna sum torque about over here, the right side of this section. So torque about over here. So there wouldn't be torque from this or this, only from this, which would be in the negative z direction. So negative 1/4 L times 1/4 F. And then let's not forget this couple, which is in the positive z direction. Okay, so now let's solve for our 3 unknowns right here. P, 0, right here. V, 1/4 F. M is positive 1/16 LF. Okay, so there we go. We got the internal forces and moment. Okay, now you don't need to, but just to prove to you, if we analyze this other section, what would we have gotten? Let's try it. Okay, so some force X, some forces Y, some torque about somewhere clever. Okay, X direction. My coordinates were like this. Okay, so in the X direction, negative P. That's it. Y direction, V minus F plus 3/4 F. Okay, let's sum torque about, how about over here, the left side. So there's torque from this. Actually, how far? I didn't label the, so 1/4 L. Okay. So here to here is 1/4 L. Here to here is 3/4 L. Right? You see. Oh, no. Here to the end was 3/4 L. So here to here, right, is 1/4. Right here to here is 1/4. Here to here is 1/4. So here to here is 1/2. Oh, yeah, I labeled it correctly. Okay. So here to here is 1/2 L. Okay, so the torque about right here is negative 1/2 L times F plus 3/4 L times 3/4 F. Okay, and then let's not forget this couple, which is in the negative z direction. All right, so P is 0. V is F minus 3/4 F. 1/4 F. M equals, this goes on the other side, all of this. Okay, so that's 9/16 LF minus 1/2 LF. 1/2 is like 8/16, so that's 1/16 LF. And there we go. Okay, so hopefully that's the same. Yep, right, so same answer either way, which means you don't need to analyze both sections, right? Just one or the other. Just pick the one that looks simpler. Okay, so spend this week focusing on just find internal forces and moments at a particular point along the beam and get really good at it, because next week we're going to do internal forces and moments as a function along the beam. So we get the internal profile along the beam as a function. So that gets a little more complicated. So just focus your attention on this first. Okay, and then I'll see you on that next video.